We're asked to solve this system of equations using matrices. So there's three different variables. There's an x variable, a y variable, and a z variable. So the typical way of handling this with matrices is to write the coefficients of each equation. So my x had a 1 in front of it, my y has a -1, my z has a 0. And we usually make a vertical bar for what it's supposed to be equal to. Some texts do that, and it looks like some texts don't. But. Okay, that's the first equation. Second equation, we put a 3 for x, a 0 for a y because there's no y, and a -2 for z. And then the third one is 0 for x, y, 2 for z, and that should equal 3. So to solve an equation, the typical approach is to get it in row-reduced echelon form, which is where we're looking for ones going across the diagonal and zeros elsewhere, if we can help it. But at some point we can stop and solve without having to try to get zeros elsewhere. So the way that works is you first try to make sure you get a 1 in the first column, in the top left part of the first column. And we're lucky. Our problem already started off with that. Now we have a 1 in the first part of the diagonal. This is already a 0. That's good. To make this be a 0, one tool we have up our sleeve is that we can take row 2, this row, and then we can subtract 3 times row 1. Because 3 times 1 makes 3. 3 minus 3 would make 0. We'll keep all the other rows the same. Okay, so row 2 is changing. Row 2 is getting, it's being subtracted by 3 times row 1. So 3 times 1 makes 3. 3 minus 3 makes 0. Now 3 times -1 makes -3. 0 minus a -3 makes +3. So sometimes, I mean, when I do this, I usually just +3, and then 3 plus 0 makes 3. -3 times row 1 makes 0. 0 plus -2 makes -2. -3 times 6 makes -18. -18 plus 21 makes 3. Okay, so this column is all set. We got a 1 in the diagonal, 0's elsewhere. Now we need to put a 1 in this diagonal and 0's elsewhere. The 1 is first. You got to make sure you have the 1 first. So I'm going to take row 2. I'm going to add 2 times row 1. Yeah, I think that's probably easiest. I try to avoid fractions. There's other ways of doing this. So if you were thinking of doing something different than my way, you might have been right. Oh, wait, no, I can't do that. Sorry. Because if you do 2 times row 1, then 2 times 1 makes 2, and 2 plus 0 would make 0. So that's not going to work. So instead, I think the best approach might be to get fractions, unfortunately, which is not pretty, but we're going to take a third. That way I have a 1 going across the diagonal here. It's way easier on paper, because writing with this mouse is tough with a lot of numbers. Everything else stays the same. The middle row is changing. Everything's being multiplied by 1/3. We don't want to mess up our 0, so that's why we had to change it and multiply by 1/3. So I multiplied. Oh, I didn't want the whole thing to be blue. I wasn't even paying attention. Sorry, but I was doing so good with my color coding. So we got a 1. Now we need to have 0's in the diagonal. So I'm going to do row 1. I'm going to add row 2 to it. And I can do that because 0 plus 1 is still going to keep a 1 in the diagonal. And 1 plus -1 is going to make 0, just like I'm looking for. And down here, while we're at it, we want this to be a 0 as well. So I'm going to take row 3 and add -3 times row 2 to it. Because I know -3 times 0 makes 0. That adds here. It doesn't mess up our zeros. -3 times 1 makes -3. -3 plus 3 would make 0, like we're looking for. And in case you're feeling worn out, we're almost to the end here, okay? So this row 1 is changing. I'm adding row 2 to it. So 0 plus 1 makes 1. 1 plus negative 1 makes 0. Negative 2/3 plus 0 makes negative 2/3. And then 1 plus 6 makes 7. Row 2 is not changing. Row 3, I'm adding negative 3 times row 2. So negative 3 times 0 makes 0. 0 plus 0 makes 0. Negative 3 times 1 makes negative 3. Negative 3 plus 3 makes 0. Negative 3 times negative 2/3, that makes 2. 2 plus 2 makes 4. Negative 3 times 1 makes negative 3. Negative 3 plus 3 makes 0. Okay, so here's where we could pause and go back to an equation land. This says that 4z's equals 0. So that tells us something. Z can't be anything. Z has to be a specific number. Z has to be 0. And then we can use that in this equation. This equation says 1y plus negative 2/3 z equals 1. But we just found out that z is a number. Z is just one number. Z is 0. So that means this, you plug in 0, multiply to 2/3 is gone. 1. And then to find out what x is, we could go back to this top equation and retranslate it. This is 1x. Subtract 2/3 z equals 7. But again, z is 0. So that means x has to be 7. So to answer this question, those are the numbers. You would plug them in x, y, z. So we had x was 7, y was 1, and z was 0. So 7, 1, 0 goes in here. It would have infinitely many solutions if we had something like a true statement at the end. Like, let's say these are all the same, the first and the second row, and the third row came out to be something like 0 equals 0, right? In that case, it wouldn't matter what z would be, right? Because 0z equals 0. Z could be any number. Z could be a billion, and it would still work. So that would be a situation where z is any real number, like this option up here. Yeah, and there's a few other cases where y is any real number, z is any real number. That would be if you had matrices like this, where it was like you could translate an equation to be 0y plus 0x, 0z equals 0. Then y could be anything and z could be anything because they're both being multiplied by 0. So yeah, make infinitely many solutions happen, but let me see. So here's an example of if you're trying to boil it down and get it in row reduced echelon form. If you stop and see this, it would translate to be 2y plus 4z equals 5. And this bottom one is the same thing, 2y plus 4z equals 5. Right? So there's an infinite amount of y's and z's that make that be true because they're both like the same equation. You can y-axis is the z variable. These would be two lines that are right on top of each other. There's an infinite amount of x's and y's that work for this system here. So a value for x that would work for one particular x. I think there's also going to be an infinite amount of x's that would work for this one too. So if you saw a situation like this, there's an infinite amount of solutions for all of these variables. There's just a particular way you could phrase them. You could make them into an equation.